You are viewing one of 10 modules developed through a project funded by Geoscience BC focused on direct-use geothermal resources in British Columbia. This follow-up project was carried out between August and December 2016. The project was executed by Tuyaterra GeoCorp. These modules were developed from the Direct-Use Geothermal Resources Roadmap published by Geoscience BC in June 2016. They incorporate additional educational material that were developed as part of the current follow-up project. The voices you will hear narrating the module are myself, Catherine Hickson, and my colleague, Juliana Proenza. In this third module, we're going to be focusing on exploration techniques. You can go back and find on the website all of the modules, and they are meant to be done as a chain of work that you go through, but they can also be accessed individually, and there will be some repetition because of that. So this one is, we're going to be talking about exploration techniques from geothermal power to direct use and GeoExchange. So what is important is to understand that there is a value chain. How do we go about development? And a big piece of geothermal development is exploration. Then we're going to be talking about the methodology and then how we're actually going to extract this power from the ground. And just to remind everybody that there are two pieces to geothermal. One is the temperature, another is the cost. So GeoExchange systems are the least expensive. They use the heat capacity of the ground as opposed to extracting hot fluids from the ground. So they're cheap and easy and can be used basically anywhere where you've got ground that is gravels and sands, soil, that kind of thing. Direct use and power plants, what we need to do is extract the heat from circulating groundwater and bring that to the surface. So as we go to the right on this diagram, expenses increase and as well the temperatures increase. So in terms of geothermal development, there are many things that need to be taken into consideration. Initially, no matter what we're doing, whether it is a low temperature or surface exploitation through GeoExchange and heat pumps, or it is for power generation, we need to have permits and access to the ground. Depending on your jurisdiction, these are different. And there's a module where we will be addressing the permitting process. Once we have access to the ground that we're interested in exploring, then we need to do the exploration, and that involves geology and geophysics. Once we've done that, then we need to identify what is our resource, how deep it is, and how hot it is. That's the whole point of our exploration. How hot and how deep. Because it is those critical questions that need to be answered in order to decide what kind of a development we're going to have. Are we going to have temperatures which are relatively low and are useful for direct use, such as space heating? Or do we have power potential? Do we have temperatures that are high enough that we can produce power either by binary or by a flash system? Or do we just not have enough warm waters deep down that the only thing that we can do is to have a ground source heat pump system? So these are all decisions that need to be made before we can proceed with the kind of development, as well as understanding what the financial obligations are going to be to do that. So let's talk first about geothermal exploration. Now this section is focused on the geothermal exploration that is required for medium to high temperature resources that potential would be useful for power generation. So what do we need to do? Well, there's a lot of pieces that are important for geothermal exploration. We need to understand what existing data is available out there. The geology is obviously incredibly important. As you learned in the earlier modules, the high-temperature resources are usually centered around volcanic areas. So understanding what that volcanic history is, the age, the extent, and the kind of volcanoes is incredibly important. We also need to understand the structure. If you recall, I talked about rainwaters falling on surrounding hills. Those rainwaters then percolate through the ground, and to do that there must be permeability, and that permeability can be naturally occurring, such as you have in sand and gravel, but also it can be imposed on the bedrock through faulting and fractures. So once we understand our geology a bit better and we're focused on an area that would be of interest, we need to do some geophysics. And geophysics is a variety of things are done, but geophysics is our way of looking deep down below the surface without actually drilling. So the price to do geothermal exploration in terms of the geophysics is much cheaper than it is to drill. So first we do geology, then we do geophysics, and if we're lucky and there are surface manifestations, either springs or geysers or fumaroles, then we sample those. And the chemistry that we obtain from those particular springs or geysers or fumaroles are very important because they tell us what the temperatures of the reservoir are. Those temperatures are very important because we need to understand what is the potential temperature if we drilled into this reservoir and then can use that heat to run turbines. So we need to make a decision about whether or not this could be a binary system, or it could be a flash, or even a dry steam system. So the geochemistry of the waters is a very important part of what we have to do. Once we've put together the geology, the geochemistry, and the geophysics, then we can integrate all of this information and produce what's called a conceptual model. And that conceptual model will tell us what are the likely temperatures we're going to encounter, how deep we're going to encounter them, and what is the potential size. Once we've done that, then we pick drilling targets. We now, on the basis of our conceptual model, can look at the subsurface, and we can look at that subsurface as to where's the most likely spot that we are going to hit the temperature of fluid that we are interested in. Then we have to do exploration drilling. We need to test those targets. So in the previous slide, what you've seen is all of the geoscience that needs to be put together to create our exploration plan or a process. Now in that process, whether we're talking about geology, geochemistry, or geophysics, we're collecting a huge amount of data. So an important part of that exploration process is managing that data and managing it in a way that it can be useful to help us decide what kind of development this resource is potentially possible to create. So on the diagram that you see here, the focus here is what kinds of data processing do we need to do in order to understand what our development potentially could be. So for the geophysical data, geoscience data in general, we use programs like ArcGIS. But what we want to do is look at, okay, if we have a resource of a certain temperature, what essentially would be the demand of that? And we need to use programs such as something like MATLABs. But an important program that's focused on here is GeoFires. So GeoFires is actually helping us understand what the cost effectiveness of our exploration is going to be, and eventually into our development plan. So the slide here is simply to bring to your attention that there is a great deal of data that is part of your exploration program that needs to be handled and output to help you in your development process. Now, this process goes on over a number of years. And on this diagram, you see kind of a 5-year plan. Initially, it's only a few months to identify where potential areas are, but we need to explore them. And that's 6 months to a year, something like that. But the drilling itself can be significant depending on the size of the field and the depth to which the drilling is going to occur. And that can take a year or 2 years or longer. Once we have that physical information about the subsurface, then we need to make the decision to build, and then we go forward with what our development is going to be. Now, for power generation, this is not a bad time frame, about 5 years from identification of the resource to, in fact, producing power. But the blue arrows are meant to represent, if we're talking about a direct use resource, these are usually smaller, shallower, and not as complicated to explore for. And so this time frame is reduced. And that's a very important aspect that you need to take into consideration. Power generation is relatively high risk and expensive. Direct use exploration can be lower cost and at commensurate lower risk. So here are those elements that I've already spoken about. There's our geological data, our geochemical data, and our geophysical data. We gather all of that information together and we produce that conceptual model. And again, that conceptual model provides us with an idea of the size, the depth, the type of fluids, and in particular the temperature. From that, we're able to do a resource estimation. And a resource estimation is just an idea of how much resource is there. What are the temperatures? What are the potential flow rates? How much power could we, in fact, produce from this particular resource? Then we are able to go ahead with exploration drilling. And note the cost increases as well as the length of time to accomplish all of these various facets increase as we move down in this diagram. So let's talk a little bit first about geological surveys. For the high temperature resource, there's a very high risk associated with the development of power fields, and that has to do with the amount of fluid and the temperatures that are required to make power production economic. So we need to spend a significant amount of time and certainly money, but less money than it would cost us to drill, but we need to focus on the best places to drill so that our drilling success is higher than the global average of 50%. How do we do that? Well, one of the things we do is we do geological surveys. We map the ground. We try to define the areas that are the most likely to be the most prospective, and what we mean by the most prospective, to have high temperatures as well as fluids. And we need those fluids in order to efficiently capitalize on the resource that we have. So what you see here is a geological map. This is of an area in Chile called Maule that Altera Power has been working at development. This is where I led a team, and we did all the initial exploration work in that area. And what we did was the geological mapping, and you see that various geological units are shown here in the colors, and then you see these darker blue lines, some with arrows, and those are fractures and faults. So they are the important conduits for what we think the reservoir could, all those fluids could follow those fractures and faults. The reservoir itself is shown as this green butterfly shaped, and this green butterfly has come from a combination of the geology, but in particular the geophysics. What you see on the right-hand side, or in the center here, is a cross-section. So we've taken this area and we've sliced and put it on its side. And what you see here, this red, is a theorized magmatic intrusive body. And that is what is heating the waters in this area and producing this field. This field is called the Mariposa Geothermal System. It got its name because of this butterfly-shaped anomaly that indicates where the resource might be. Now, in Chile and in many other places around the world, there are manifestations at the surface, either hot springs or geysers or fumaroles. And you can test these with a number of different methods. What you see in the pictures is a small little unit which measures the gases directly coming out of the fumarole or out of the ground. In other cases where you have a high temperature fumarole, you collect the material in a gas flask that is shown up here. And in other areas where it's a hot spring, you simply collect the material in plastic bottles that either are treated or untreated. And what you're doing is you're trying to understand what is in that liquid, what is in that fumarole, what is escaping from that reservoir, and what can it tell us about the subsurface resource. So we look at whether or not there might be boiling in the system. What is the conductivity of that fluid that's coming to the surface? Does it have a lot of dissolved solids in it? All of these tell us something about what the subsurface is, and in particular, what its temperatures might be. So it's a very important aspect of geothermal exploration. So based on what we find, there are a number of plots that have been developed by researchers around the world which indicate what the temperatures in the subsurface might be. So the one on the left, this is from gas geochemistry. And what we're looking at is carbon dioxide and argon, as well as hydrogen, that is dissolved in the gas. We can then plot up those chemical compositions on a diagram like this. And then what we see is an indication of what the temperatures might be in the subsurface. So you can see in the case where we have fumaroles, the temperatures potentially at depth can be quite high. And in this case, what we're looking at are fluids which are more than 250 degrees centigrade. We can also look at the deuterium levels. So this is oxygen, which has deteriorated and has a particular chemistry. And from that chemistry, we can tell something about the temperatures in the subsurface. So again, this is important information that allows us to look into the reservoir in a different way than having to drill in it, which is extremely costly. Now, I've mentioned geophysical surveys. So geophysics is a variety of ways of looking at the subsurface without having to drill it. And in those, there are three main types of geophysical surveys that are used for geothermal energy exploration. This is gravity, magnetotellurics, and magnetics. So gravity is fairly self-explanatory. But in a geothermal reservoir, what happens is the rocks are dissolved, and those dissolved rocks, this dissolved material is found in the brines, and those brines then move away from where the geothermal system is, cool, and then can deposit those dissolved solids. And what you tend to have is you have buildup of either calcium carbonate or silica, depending on the kind of system you have and its temperature. So you can add gravity to some areas, while at the same time it's taking the gravity away, it's taking mass away. is gravity is the way of measuring the mass of an object. So by looking at the gravity in detail, we can tell something about how the mass is distributed within the system. So it's important in terms of telling us how that system has evolved over time and where there may be either a gravity deficit, material has been moved away by circulating waters, or it has been deposited because it's on the cooler fringes and that silica and carbon dioxide is coming out as calcite and silica, building up mass in other areas. Now, magnetics is somewhat similar, but what magnetics is telling us is what is the magnetic signature of the rock. So if we're thinking about those hot water which is circulating in the subsurface and it's dissolving rocks, one of the things that hot water attacks very readily are minerals such as magnetite. Magnetite is an iron oxide, and magnetite gives a magnetic signature to the rock. If there's a lot of magnetite in a rock, such as, say, basalt, then it has a very strong magnetic signature. If it's a quartz sandstone, it has a very low magnetic signature. So the alteration process, as well as dissolving things like silica and quartz and feldspar, will also dissolve things like magnetite. So it changes the magnetic signature of the rocks. And in general, it will decrease the magnetic signature of the reservoir rocks. And so we can map out a reservoir which has been subjected to alteration by using its magnetic signature. Another very important technique for geothermal exploration in high temperature fields is magnetotellurics. So magnetotellurics is kind of a combination of the magnetic signature but also using the electrical signature of a rock. So if you can think of a power cord and we plug a power cord into one part of the rock and we try and measure the current which is coming out at some distance from that rock, that gives us an idea of its conductivity. How well can that rock conduct electricity? So if the rock happens to be high in things like magnetite, then it will conduct the electricity very easily. If, however, it's very high in things like clay, that electricity is not conducted very easily at all. So in the alteration process, we have destroyed the magnetite and we've created clays and silica which are not very conductive. So we can use the technique of magnetotellurics in order to map out the alteration areas that are associated with the geothermal reservoir. We have to put all of these results together, and by putting them together, we are able to show what that field might be. So in this middle diagram, you see the dashed area on here, and that's a combination of an interpretation of the magnetotelluric results, as well as the magnetic and the gravity results. And what they indicate is that within this purple dashed area, these lobes suggest that there is a highly altered geothermal reservoir below the surface. So what we do is we put all of this information into a conceptual model. So what we have is we have our geophysics, which have allowed us to see deep within the surface of the Earth. We have our surface geology, as well as our structural interpretation. And when we project that into a cross-section, what you see from the colors here is a measure of the resistivity of the rock, or the conductivity. Because geothermal systems developed what is called a clay cap, and that clay cap is a result of the alteration of the rocks, the breakdown of the magnetite, breakdown of other rocks, and the deposition of carbonate as well as silica. You create this clay cap, which holds in and confines your geothermal reservoir. So below here we have our intrusion, which is creating a lot of heat. That heat is being conducted away, and then the underground subsurface aquifer, the waters are taking it away and creating a geothermal reservoir. That reservoir can then be tapped by drilling. So here in British Columbia, there has been exploration that has been done for high temperature resources. And one of the areas is on Mount Meagher, which is north of Vancouver, just north of the town of Pemberton. Mount Meagher is a volcanic complex that has a very significant geothermal system. A few years ago, Juliana, also working on this project, completed a conceptual model of Mount Meagher, and that's what you're going to see next. So in this model, she's put together all of the information that we know about around Mount Meagher, and this is the next, the last step in determining drill targets.
So what we're looking at here is just a series of data that have been put into a software program and allows you to look at this data spatially in 3 dimensions. So we're looking at the geology here on the surface with the topography underlaying. We're also looking at the locations of the hot springs in circles there and the locations of the drill holes in white squares. There was also a series of maps made during the course of the work in the 70s and 80s at the Mount Meagher complex, and these maps were basically put into their particular locations, and some maps were plan maps, so those are the horizontal maps, and some maps were cross-section maps, and so those are the maps that you see vertically cross-cutting the 3D space there. What we're looking at here is all of the drill hole locations and the temperature survey data that was taken downhole. So as we use this temperature data, you can use it to provide a 3D model of what the geothermal reservoir looks like when you connect all of this temperature data together. And so what we're seeing here is that there is something controlling the flow of heat to the surface at one end in particular of the volcanic complex. And as work was done in this area, there was a series of faults or fractures that were identified that were interpreted to be controlling this fluid flow, and they essentially coincide with the location of hot springs in the area as well. So now we will just be zooming back out. You can see the isosurfaces that essentially represent surfaces of the same temperature. And now we're just zooming out to the vertical cross-section of the complex, showing all of the data together.
So now that you've seen the conceptual model, what we do when we've completed that model is we're now able to identify the drilling targets. And this now starts the most expensive part of our geothermal exploration process. Because in terms of drilling, we need to get our rigs to the area. In many cases, these areas are remote. They do not have existing roads, so we need to build the roads. We need to figure out what kind of rigs that we want. Do we want a small rig that is going to give us gradients? This is an inexpensive way of understanding how hot it might be below the ground. And we also need to delineate. So once we start drilling, we need to understand how big is this resource. When we encounter the resource, then we need to test the wells. And once we've done that, we understand what are the temperatures, what's the size of the resource, then we start plant building and commissioning. What you see in the figures, this is a small coring rig. that was used to drill in Chile, and these holes were small holes. They were, depending on which well, there was a number of wells that were done, but they were up to a maximum of 4 inches in diameter. The drill on the right-hand side is a full-sized drilling rig. You might even see this kind of rig in an oil and gas field, for example. So it's able to collar holes of large diameter, 22 to 36 inches, and then drill down at great depth into the reservoir. And at those depths, the production casing can be anywhere from 9 to about 13 inches in diameter. So this is a rig that is brought in once you understand what your resource is and you have identified what the depth is that you're drilling to and the temperatures. And then it makes this kind of drilling worthwhile. So these wells, as you can see, so here is just a schematic cross-section of what it looks like. And the well itself, in terms of the diameters that you see here, and by convention, the diameters are all given in imperial units, and that's because of the dominance of the U.S. oil and gas industry on well drilling. What you see here is called an engineered well. So once you understand the depths that you're drilling to and the temperatures, and you've made a decision about how big you want your production casing to be, then a well design engineer goes in and designs your well and makes decisions about how big the top of it is going to be, what parts need to be cemented. As you see down here, this stippling is what indicates what parts need to be cemented, and then where your production casing is going to be. This process is expensive because you need to really understand what your reservoir is going to be, but incredibly important. You need to drill the right-sized well to extract and get the information that you need from deep down in your reservoir. In today's geothermal world, a lot of wells are drilled directionally, and this is what you see shown here schematically. The well starts out vertically, but our target is not directly below the well, but is some distance off to the side, and that's why you see this kink in it, because it is bent. Now, wells in the geothermal world are typically from 1,000 to 3,000 meters. And you can drill multiple wells from a single location. The location is called a pad, and that pad can have multiple wells and multiple wellheads from it. So if you look at this diagram where we have this well deviated off in this direction, you can imagine from that same platform we can have a vertical well, or we could have wells that deviate off both in an east-west direction as well as in a north-south direction. And this can help cut down the costs of developing a field by having multiple wells from a single pad. Before Juliana takes over, let's go through a typical geothermal. So this is a call this a medium to high temperature power application. So in the work that we've done, we've drilled into our geothermal reservoir. So it has been defined. We've seen and developed a conceptual model. From that conceptual model, we've decided where our drill targets are. And we've defined our geothermal reservoir, shown here in this greenish color. So here's a production well. And what we're doing is we are drawing out, and what you see in terms of the dashed versus the solid line is that dashed part of the well is what we call the production casing. And that production casing is where we're producing the geothermal fluids from. So in this case, you can see those geothermal fluids are entering the well over a very wide or long part of the well. Here, though, they are in not being produced because this is cool. The fluids over here are cool and they would affect the way we produce this power. So we're drawing up the geothermal fluid. It then goes into what's called a separator. There are very few fields which are what we call dry steam. Most of them are coming up as a certain percentage of steam and a certain percentage of brine. So we have to separate them because we can't put water through our turbine. We can only put steam through it. So in the separator, we remove all of that water, and that water, or brine, is then pumped back into our field, and the steam is then used to run the power plant. So most of the brine that is extracted still has a significant amount of heat in it. And so in many applications, that brine is being used for other direct use applications. And much of that brine can be used to do things like heat the buildings around the plant. They can be used to heat up greenhouses or dry vegetables. And you could develop a resource park around both aspects, power generation as well as the direct use. When the water is below useful temperature, then it is reinjected back into the reservoir. In fact, not into the reservoir, but just on the margins of it. And this continues to regenerate the system. So that cool water, which is pumped in, will then circulate back through into the reservoir. And as it does so, it's heating up until it is at temperatures that are worthwhile to produce it. However, it should be noted that this reinjection is a tricky thing to do, and every reservoir is different, and every reservoir will need a fair amount of work to optimize the reinjection versus the production of that field. So now Juliana is going to take over and talk a little bit more about other aspects of geothermal heat extraction.
Thank you, Kathy. So as Kathy has gone through the more complex process of extracting heat from the ground for power generation, you can imagine that the process for direct use utilization would not be as complex. So as Kathy went through the idea that when you have a hot fluid and it's a mixture of vapor and liquid, you are separating it through a separator, and then the rejected fluid that isn't used in the power production side of things can be utilized for direct use applications such as greenhouses, etc. So if you have fluids from a geothermal reservoir or from a hot aquifer that are not hot enough for power production, they can still be extracted and used for those same type of applications such as greenhouse heating or industrial processes like lumber drying or produce drying or aquaculture. So the process is essentially that you still have a production well and a reinjection well where you're extracting water from either an aquifer or a geothermal reservoir, and that water is then pumped up and goes through a series of components of the geothermal system, which is typically heat exchangers and pumps, and in some cases we'll also utilize heat pumps at the surface to have more efficient heat distribution. And then that heat is distributed through the area that the heat is used. So it could be for district heating if it's close enough to a community, or it could be utilized for buildings that are in the area that are commercial, or like we've mentioned, greenhouses, etc. And so oftentimes there is a market that is known that this resource can be used for. And if there is not a current market when you are exploring and developing a resource, you have to establish that that market can be brought forward and invested in, and that you will have returns with that market. And so there is quite a complex financial process in that case. But if you already have a market, for example, if you already have industrial processes in the area that can utilize a resource, then the economics increase much more favorably because you don't have to spend money in actually developing the infrastructure for the market and uses that you are developing. So basically what we've got here is we've got a schematic that shows how a direct use heating system would look like. And so you've got a couple of different ways that the heat could be extracted. The fluid could be extracted from a production wellhead and pumped from the well and used directly or through a heat exchanger to transfer the heat from that fluid to whatever application that you're utilizing it for. Or alternatively, in the well, you could actually have a downhole heat exchanger that is installed in the well, and through that downhole heat exchanger, a secondary or a binary transfer fluid is used to instead extract heat from the ground up to the surface and then transmit it to whatever end use process you're utilizing it for. So again, you can see how the lines can be blurred with GeoExchange, where you're essentially using another medium to extract the heat from the ground, which is your secondary or binary transfer fluid, or in the case of direct use, you are utilizing the fluid directly for a process and then re-injecting it back. So here you've got an example of heat extraction through a large GeoExchange vertical borehole field. And this is an example from a campus in the United States. And so you've got two borehole fields at opposite ends of the campus that are extracting heat from the ground at, and in the text here, when they refer to degrees, they are talking about Fahrenheit, not centigrade. And so in this case, they are using downhole heat exchangers with a secondary fluid, and the heat is being extracted from the ground, transferred to that binary fluid, and then as it comes up, the heat is then again exchanged through heat pump systems at various points within the system. We've got the red and the blue here, which symbolizes the hot water loop and the cold water loop. And if you went through Module 2, you would have seen this slide. And again, we're just really trying to showcase here that heat extraction can happen at a more dense or high energy use level where you've got a lot of buildings or community that you're utilizing the heat for, or it can be used at the residential level. And there are different types of configurations. You could be using an aquifer and utilizing that water directly. You could be using downhole heat exchangers in a well that are tapping into the ground. You could be using surface water loops that are actually extracting water from the constant temperature in a body of water. Or you could be using matrix of ground heat exchanger in vertical boreholes, such as the example that we just went through in the past slide. And so what you've got here is that at the residential level, you actually have an example where the water is used directly in this case, and that's really quite rare. Typically at the residential level, you would have horizontal coils or horizontal closed loop as the cheapest systems because you're not drilling. And then if you don't have the surface area around your home and have the upfront capital to invest in a system that is a bit more expensive, you can drill a bit deeper, a couple of boreholes or 3 boreholes, depending on the heat requirements of the home, and use the heat that way. So again, 4 ways of geoexchanging. You've got the open loop using a body of water, and this is at the residential level again. So just showcasing these different types of systems at the smaller end of the range and how In this case, one of these examples is actually utilizing the water directly. So we've gone through extraction and exploration methodology for, again, the spectrum of geothermal. So in often cases, if you're only utilizing the fluid from the ground for just one end use, the economics are much more expensive. That's why, for example, for at a home level, it's a very high upfront cost for one homeowner to put up, about $30,000 or $40,000, which is what a system would cost for a typical home if you're drilling a borehole, or maybe $20,000 or so if you're putting in a surface loop just below, 5 meters depth. So those are quite high costs for an individual family to bear. Whereas the larger the scale of the system, the larger the scale of the end uses, the more people you've got on board, the more customers you have on board for a resource, the economics become much more favorable. And so those are the areas typically that are favored for exploration. And those are the areas that typically move forward through development. But as we have shown, these systems can be economic at different scales, and that's important to note. So that's the end of this presentation, and the next one will be Module 4, Development Steps.